Hello, Mr. Collier here. This is the final set of notes for Chapter 5. This is Section 3, Net Force and Equilibrium. There's three main objectives for this lesson. We're going to learn how to calculate net force, define equilibrium, and learn how to draw free body diagrams. So it's rare for there only to be one force acting on an object. Commonly, they're going to have a lot of different forces acting on any given object in motion, and it's the interplay of all these forces that determines what actually happens to the motion of the object. So here is an example. We have an airplane flying through the air. It's got thrust, drag, lift, and weight, and those all play together. So let's look at each one of those. Weight is a force that pulls an object down, and that comes from gravity acting on its mass. Drag is a force of friction, which will resist the motion. In this case, the airplane was moving to the right, so drag is to the left. The thrust of the engines, which is going to propel it forward, and the lift, which is actually a force that comes from the flow of air over the wings, lifting it upward. And it's all these forces acting together that determine whether the plane's going to go up, down, speed up, slow down, etc. The term for this is net force. Net is a term that means sum, and so the net force is the sum of all the forces. Because force is a vector, the net force is also going to take into account the direction of all of those forces. So in this example, we have an airplane with 55,000 newtons up, negative 50,000 down, so in opposite directions they will subtract, giving you a net force in the upward direction of 5,000 newtons. So what direction is the plane going to go? Well, it's going to go up, and this is how airplanes rise, by creating more lift force than they have weight. Looking real briefly at the forward and backward forces, you've got 20,000 newtons of thrust from the engine and 20,000 newtons of drag from the air resistance. So in terms of forward and backward motion, the airplane's going to be moving forward but at a constant speed with no acceleration. When you have more than one force acting on an object, there's really only two things that can happen. You can have the net force equal to zero or the net force not equal to zero. When the net force is equal to zero, it's because the forces have balanced. Like in this case, you've got 10 to the left, 10 to the right, the two forces balance, and you have a net force of zero. And in example number 2 here, you've got 10 to the right, 7 to the left, they don't balance, the net force would not be zero. When the net force is non-zero, the object's going to accelerate in the direction of the force. So in this case, you've got a net force to the right, the object will accelerate to the right. When the forces are balanced, the net force is zero. So in that first example, 10 to the right, 10 to the left. That would be an example of balanced forces. When the net force is zero, we say that the object is in equilibrium. And when an object is in equilibrium, it has zero acceleration. So it's either going to continue to be at rest or continue moving at a constant speed. For example, the book in this picture sitting on the table, the forces acting on it are balanced, so the book continues to be at rest at the table. If the forces became unbalanced, it would start accelerating in some direction. When you look at a book on a table, it's easy to picture gravity pulling down on the object. But it's a little trickier to understand that there's actually another force acting on it, which is the force of the table pushing up on the book. That's called the normal force. In this case, normal means perpendicular, and that's exactly the case. The force is perpendicular to the object. The normal force is going to be equal in strength to the force pressing down. Because of that, it's sometimes also called the support force, right? Whatever weight the book pushes down on the table with, the table pushes up on the book, supporting it and keeping it in equilibrium. To help us better understand the many different forces that can act on an object, we will often draw something called a free body diagram. A free body diagram will usually start with some representation of the real life situation, like these books on this table and the weight of the table. When drawing a free body diagram, you're taking the real-life situation and turning it into a bunch of arrows representing the different forces. So thinking about this table, it's in equilibrium. All the forces acting on it are balanced. It's not accelerating. It's just sitting there. And so it's easy to think about the downward forces, right? The weight of the table pushing down, the strength of this additional pile of books pushing down. But then the table's not moving, so there must be normal forces, and they are spread out over each of the legs of the table. And when you look at the sum of all these forces, if you total the downward forces and total the upward forces, they are equal and opposite, and hence the object is in equilibrium. Based on knowing whether something is in equilibrium or not, you're going to be able to do some word problems. For an object to be in equilibrium, we've defined that as all the forces adding up to 0. So you can see a simple question like this: is this object in equilibrium? So look at each direction independently. Going up, we've got 4 plus 6. We've got 10 newtons up, 10 newtons down. So right there, those are balanced. Those are in equilibrium. 20 newtons to the right, 20 newtons to the left. Those are also in equilibrium. So we would say, yes, this object is in equilibrium. The forces acting on it are balanced. Here's another example problem. 2 chains are used to support a small boat weighing 1,500 newtons. One chain has a tension of 600 newtons. What is the force exerted by the other chain? If you're ever having problems picturing something, I think it's always best to give it a draw. So here is a diagram of it. We've got the weight of the boat is 1,500 newtons. One chain is supporting it with 600 newtons. So now what is the tension in the other chain? We know that the total tension in both the chains is going to be 1,500 because we know that the boat is suspended, it's motionless, so the net force is 0. So 600 plus the tension of the second chain is equal to 1,500. You solve for the unknown. 900 newtons is the tension in the other chain. That is it for net force. You're going to add up the forces in the same direction, subtract them in opposite directions, and if the forces are balanced, the acceleration will be 0. In Chapter 6, we're going to talk about how to know what happens when the acceleration is not 0, when there is a net force. How much will an object accelerate?